So we talked about intermolecular forces on Wednesday, and really the prerequisite stuff, all of that, some review stuff from 123, that plus the intermolecular forces. That's all you'll see on the Alex Quest. Okay. Um, but those intermolecular forces tell us a good bit about the physical properties of some of our compounds. The first that we'll talk about here is the surface tension of a substance. And so when we talk about surface tension, we're really talking about how well those molecules that are at that surface between the liquid and the air interface, how well those molecules hold together. And so if we look down here at this circle, this interactions here, that molecule in the middle is able to interact with all the molecules around him in a sphere, right? If we sort of imagine our molecules as being these little balls, in 360 degrees, he can interact with neighboring molecules. Okay, but when he's at a surface, he still wants to have that interaction, but that interaction can only happen on one half of that molecule, right? The half that's actually touching the water, touching the bulk of that solution. The other half that's touching the air can't really interact. It's not that things in the air don't interact well with whatever the liquid is, but more often than not, gas molecules are moving so much faster than the liquid molecules. And so even if they do interact, they're going to move around, they're going to move away before that interaction can sort of really hold that molecule there or be a permanent interaction. Whereas the interactions that it has with the liquid around it are more permanent, they're long lasting. And so the stronger the intermolecular forces are, the more energy it takes to break that surface tension, right? And hopefully that should make some sense to us. So just generally speaking, if we have stronger intermolecular forces, and again, remember I'm going to abbreviate that IMFs, then we have higher surface tension. Have any of you ever done that experiment where you put pennies or paper clips or something into a very full cup of water and see how many you can get? So because water is able to hydrogen bond, and remember hydrogen bonding is the strongest intermolecular force we have. So because water has that very strong intermolecular force, he's able to really have a strong surface tension, and you can put a lot of pennies into a cup of water. The other thing I'll say about water is, in particular, water forms 4 hydrogen bonds. Let me go to the next slide, actually. So water is sort of a special case. Water forms 4 hydrogen bonds. This is really hard to see in this diagram, but this water molecule here, I'm going to put him in sort of a green. So this water molecule right there, right, he has 4 different hydrogen bonds that he's making. So he's making this hydrogen bond over here, this hydrogen bond over here. Those are both, those are both to the to hydrogens on neighboring water molecules. And then he's making a hydrogen bond here from his hydrogen to a neighboring oxygen. And then the one that's hard to see is sort of behind the molecule, but it's to that hydrogen there, to that oxygen there. Right? So water can make 4 hydrogen bonds which is, remember, hydrogen bonds A are very strong bonds, and water is able to make 4 different hydrogen bonds. And so that's another reason why the surface tension of water um, is so large. The reason that ice floats, ice is less dense than water, is because when we slow those water molecules down, so if you remember back in chapter 5 when we talked about gases, you talked a little bit about kinetic molecular theory, and you talked about how as the temperature of a substance rises, the speed of those molecules increase. Right? In chapter 5, we talked about it in terms of gases, but it's true for most compounds that as we increase the temperature, the kinetic energy goes up. And so the opposite is true as well. As we decrease the temperature, the kinetic energy of those molecules goes down. And so for water, when it's liquid water at, say, room temperature, those water molecules, they're not moving as fast as gas molecules, but they're still tumbling around in liquid water. They'll have a hydrogen bond and then they'll move and that one will break, but the next one will form because they're near to that molecule now, and they roll around, and hydrogen bonds break and form all the time, right? Kind of like a politician going through a crowd shaking hands. Okay. But as they slow down and slow down and slow down, we sort of lock into place in this crystal structure. And so here's this 3D structure of water. Okay? And so as a solid, water can sort of hold on to all 4 of those hydrogen bonds. Right? So all 4 hydrogen bonds, I'm going to use the word stick, right? They're all being used. All 4 of those hydrogen bonds are being used. Whereas again in water, they make one and then they break it, and so on average they have less than 4. You know, they have 3, let's say. I don't know what the number is off the top of my head, but it's say there's only 3 hydrogen bonds on average in liquid water. There's 4 hydrogen bonds on average in solid water. Because those hydrogen bonds sort of have a very definite energy. Remember we talked about how the length of a bond is sort of set. We talked a little bit about that in chapter 10 when we talk about bonding and molecular geometry and things, about how a single bond is longer than a double bond, is longer than a triple bond. And for a given pair of atoms, that bond is set length. Same is true for hydrogen bonds, even though they're not really bonds. For a hydrogen bond in water, it's a set distance. And so because hydrogen bonds sort of keep those molecules a set distance apart, they can't get any closer like they would if it was liquid water and they were moving a lot. They're sort of locked into this crystal structure. And it turns out that they're on average farther apart in the crystal structure than they are in liquid water. And so that's why ice is less dense than water, because they're less closely packed. And so these molecules are less closely packed. In ice versus liquid. And there are certain people out there who will say that that one fact is the reason there's life on Earth, right? Because if ice was more dense than water, then in the wintertime, ice would freeze and sink to the bottom of your lake or of the ocean. And then in the summertime, the top of the lake or body of water would be warmed up, but it wouldn't ever warm up the ice on the bottom. And so the next winter, you'd get more ice and it would sink to the bottom. And then you'd get to this point where most of the ice in the ocean, or most of the water in the ocean is ice at the bottom, and you just have this little livable layer on the surface. And so most of the water would be sort of encapsulated in the ice in the oceans, and we wouldn't have things like icebergs and glaciers and all that fresh water on the surface. So there are some people who argue that this one fact of water is the reason why we have life on Earth. All right, but moving along. So all of this sort of ties into phase changes. So the more energy we have, the faster those molecules move, The faster they move, the more they want to be apart from one another, and vice versa. The slower the molecules move, the more likely they are to interact with one another. The more they interact with one another, the more close together they're going to be. And so when we think about phase changes, as molecules slow down, the intermolecular forces can function better. Right? If I am, if we're interacting, if we're moving very quickly, right? Again, shaking hands is not a perfect analogy, but it's pretty good. If you're moving very quickly, you can't shake that many hands, right? Maybe you shake every fifth person because you're moving real quick. And if you're a marathon runner or something and you're really running, you're not shaking anybody's hand, right? And so as you slow down, as you spend more and more time with neighboring molecules, as you slow down, you're going to have more of those interactions. You're going to be able to stop and shake more hands. And so as those molecules slow down, there's more opportunity for intermolecular forces to engage. Right? And the more those intermolecular forces are actually holding those molecules together, they condense. The substance condenses. So if we start as a gas and we take out some of that heat energy, some of that thermal energy, we remove it, we cool that gas down, right? What's going to happen is that those gas particles, they're moving a little bit slower, and then two water molecules in the gas phase meet up and they say, you know, these hydrogen bonds that we're able to form, that's better than being apart because now we're moving slower. And then as they all do that, right, think about millions of water molecules, they all pair up first and then their droplets get bigger and bigger. And then you have this condensation and it forms a liquid. And in the liquid, things are still moving, right? Those molecules are still moving around, but as they get colder and colder and they move a little bit slower and a little bit slower, at some point they get to the solid and they say, man, let's just really slow things down and instead of a handshake, man, let's have a conversation. Let's sit down and have a cup of coffee. Now in a solid, unless we're at absolute zero, molecules are still moving, you know, they're still vibrating, they're still having a little motion, but they're not running a marathon. They're not even swimming in a pool. They're just sitting, having a cup of coffee, you know, maybe they cross their leg, uncross their leg. And so the sort of extent of the motion really, really goes down as we go from a gas to a liquid to a solid. And so it's these phase changes that we're going to spend the rest of our time in chapter 11 talking about and what these phase changes really look like. Okay. Our next slide here, really just goes back to what I was talking about in terms of the energy and the temperature being related to one another. This is the Boltzmann distribution. Again, you should remember something kind of like this from chapter 5 when we talked about the kinetic molecular theory for gases. At temperature 1, this is our Boltzmann distribution. And let's say that this is the energy required to go from the liquid phase to the gas phase. So remember we talked last time that this would be the delta H of, does anybody remember what it is? The difference between liquid and gas. We had fusion, vaporization, and sublimation. Which one of those three is liquid and gas?
Vaporization.
That's it, vaporization. And so this is delta H VAP. Right? And so if we're at a relatively low temperature, pull out our calculus tools, we know that this area under the curve is pretty small. And so there's a small fraction of molecules that actually have enough energy to go from the liquid phase to the gas phase. And so small fraction. And again, I know that because that's the area under the curve. Have enough energy that is, the energy, kinetic energy, is greater than delta H of vaporization to go from the liquid to the gas. Now we can draw these Boltzmann distributions really for any transition. It could be from liquid to a gas, it could be from a solid to a liquid, or it could be from a solid to a gas, right? Any of those three transitions we could draw. And so here, now that I have a larger temperature, my curve has shifted, right? There's more of my area under that curve that's now past this E1, this delta H of vaporization. Again, this is the same energy. It's still delta H of vaporization. And so at a higher temperature, we see that there's a larger fraction has our energy greater than that enthalpy of vaporization. And so there's some sort of tipping point where, you know, we know that we're at a temperature where our liquid starts to boil, right? And so let's say at T1 down here, let's say this is room temperature. If you just leave a cup of water out for a day or two or three, some of that water is going to evaporate. Right? That water never really boiled, and yet some of that water went from the liquid phase to the gas phase. That's because there's only a small fraction of those molecules that have enough energy to get out of that water, right, into the vapor phase. Now, as soon as those molecules have left the liquid phase and gone into the vapor phase, well, that distribution doesn't really change as long as we're still at room temperature. And so there's sort of a new set of molecules that has that energy. They sort of redistribute the energy, and there's now a new set of molecules that can go from the liquid phase into the gas phase. Now, that's very small, right? That area under the curve there is super small, and so this evaporation process is very slow at room temperature. But if we increase the temperature, of course, it's going to evaporate a little faster, right? If we put out a cup of water today when it's almost snowing, it's going to take a long time for that cup of water to evaporate. But if we put out a cup of water in July when it's 90 degrees, let's call it 30 degrees centigrade outside, it's going to take much less time for that same cup of water to evaporate, because a larger fraction of those molecules have enough energy to overcome those intermolecular forces and to go into the gas phase. So that point at which we say this is the boiling point, right? How do we know what that threshold is? It all has to do with this vapor pressure. Okay, vapor pressure is a term that we're going to use a little bit in the rest of this chapter as a way for us to sort of talk about the strength of intermolecular forces. And so this equilibrium vapor pressure is the vapor pressure. So the pressure of the vapor, right? Hopefully that's easy enough to understand. The pressure of the gas that is forming above our liquid, right? So let me just pressure of the gas forming due to vaporization. Now, that could be evaporation, which we normally think of as kind of a slow process. It could be boiling, which is technically evaporation, just very fast. But just vaporization in general, right? So the pressure of that gas forming due to vaporization. And you'll see here that we reach this, it's called an equilibrium, right? There is some temperature where the water molecules are, I'm using water as an example, but where the molecules of our substance are evaporating at the same rate that they are condensing. And so each compound has a different equilibrium vapor pressure, and it depends on temperature. And so each substance vapor pressure changes with temperature. This is the first time that we have talked about equilibrium, right? This is an equilibrium arrow here. Much of this semester will be spent discussing equilibrium. And so we're going to talk a lot more about what exactly equilibrium means, but let's say that we have these two different reactions happening at the same time. We have liquid water going into the gas phase, and we have gas phase water, vapor, going into the liquid phase. Equilibrium just means that those two things are happening at exactly the same rate. Right? And so for every 3 water molecules to become vapor, 3 water molecules become liquid. Right? And so that is happening at the same rate. And again, this is telling us a little bit about our intermolecular forces. If we have a low vapor pressure, do you think those molecules are holding on to one another strongly or are pretty loose if we have a low vapor pressure?
Loose. Pretty loose.
So loose and low, okay, I can see the connection. But if remember, strong intermolecular forces mean that I don't get into the gas phase very easily. If I don't get into the gas phase very easily, then my pressure is going to be low. Right? And so a low vapor pressure right? What that really means is that there's a little gas that's being formed. If we have a low vapor pressure, there's not a lot of gas being formed, and so that means we must have strong intermolecular forces because they're busy holding the molecules together in the liquid phase. And so things like alcohol or gasoline, right? These have just dispersion forces. Alcohols, you have a little bit of hydrogen bonding, but not as much as water. Gasoline's maybe a better example. It just has those dispersion forces, those van der Waals forces, and if you pump gas, man, you smell gasoline, right? There's no getting around it. But if you have something with very strong intermolecular forces, they make that they make vapor very much more slowly. If you're into perfumes at all, a perfumer will use what they call base notes and mid notes and high notes, right? The higher the note, the higher the vapor pressure. It's sort of the first thing you smell, right? The base notes in perfumes have very low vapor pressures, And those are the scents that tend to last all day because they don't evaporate very quickly. And so, this idea of vapor pressure and intermolecular forces comes into play in certain situations. Okay. So we talked a little bit about boiling point. We talked a little bit about equilibrium vapor pressure. Now we're going to talk about the molar heat of vaporization. This molar heat of vaporization, right, this is our delta H vap that we've been talking about. This is how much energy it takes to go from a liquid to the gas. Right? And so, of course, because we're talking about molar heat of vaporization, this is the energy required to convert 1 mole of our substance from the liquid to the gas phase. At its boiling point. So it has to be at that temperature. It's not just sitting out at room temperature. How much energy does it take? It's the energy required at the boiling point. And so here we have the first equation of the semester for us. We have this Clausius-Clapeyron equation, and it relates our equilibrium vapor pressure to our molar heat of vaporization, and it tells us something about the temperature. It does have this little constant C out here, plus C, right? We will often ignore that or assume that that constant is pretty close to 0, which is a reasonable assumption most of the time. If we look at the graphs here, if we look at vapor pressure versus temperature, you see that they all have very similar curves. Mercury is much more dense, and so Mercury has its curve is a bit longer. Right? But the diethyl ether and the water have similar curves. And if we look at the diethyl ether, I don't know why they changed colors, right? This is the diethyl ether. It should be red line. It's not my textbook. If we look at this graph of natural log of P over 1 versus 1 over T, you'll notice that is this Clausius-Clapeyron equation. Here's our Y, and this 1 over T is our X. And so the slope of this line, right, is delta H vap over R. So the slope is negative delta H of vaporization over R. In chapter 5, we used R with units of liters atmospheres because we were interested in volumes and pressures. Now we're interested in energy, and so we're using the R from chapter 6, where we used it in terms of joules. All right. There's one other way of using Clausius-Clapeyron if you have a change in pressure or a change in temperature. You can write it either one of these ways. This is just either algebraically related, but it's the same equation, right? And so if you have 2 temperatures and 2 pressures, you can sort of figure out what the delta H of vaporization is for a given compound. So let's remember this Clausius-Clapeyron equation and do a quick example. Diethyl ether, we just talked a little bit about that, has a vapor pressure of 401 millimeters of mercury at 18 degrees C, and we want to calculate the vapor pressure at 32 degrees C. And so we need a few pieces of information. Let me just write out our equation again. It's the natural log of P1 over P2 I know I need the 2 pressure version instead of the 1 pressure version because it gives me a pressure and asks for another pressure at different temperatures. That's equal to delta H of vaporization over R times 1 over T2 minus 1 over T1. And that's just from the previous slide, copying that over. Our units on R are joules per mole Kelvin. And so we need to convert our degrees Celsius to Kelvin. How do we do that? What's our conversion factor there?
273.15.
That's right. We add 273.15. Sig figs tells us we don't need the 1.5 necessarily this time, but we get 291 Kelvin. Okay. The other thing we need, so we have our P1. We have our 2 temperatures. There's one, T1. Here's another, T2. 32 plus 273 is 305 Kelvin. That's going to be T2. We need to look up this delta H of vaporization. Now, thankfully, there are tables and tables of this kind of data. And so if we look at the table in our textbook, delta H of vaporization is 26 kilojoules per mole. Now we have kilojoules per mole here. R has units of joules per mole. And so what should I convert this delta H vaporization to? If I'm going to go from kilojoules to mole to joules to mole, what's my new number?
26,000.
26,000 joules per mole. Okay. Now, it gives it to us in millimeters of mercury. We're really used to using atmospheres, right? But it doesn't really ask us to change it, and so I'm going to leave it. Right? It doesn't ask for it in atmospheres. I'm not going to convert it. So now we just have to plug things in. Natural log of 401 millimeters of mercury over P2, that's my unknown we're solving for, equals 26,000 joules per mole divided by 8.314 joules per mole Kelvin times 1 over 305 Kelvin minus 1 over 291 Kelvin. Okay, got to do a little algebra. We're okay with this. 1 over 305 minus 1 over 291 times 26,000 divided by 8.314. I got negative 0.493. Right? The right hand is unitless. All of our units cancel. How do I get rid of natural log? Get rid of natural log by using e to the, right? So natural number e, I'm going to raise both sides. E raised to the power both sides, so that cancels out my natural log on this side. And so I end up with 401 millimeters of mercury over P2 is equal to E raised to the negative 0.493 is 0.611. So I just rearrange and solve for P2. Now, before I write this answer down, I'm increasing the temperature. Should that increase the vapor pressure or decrease the vapor pressure?
Increase.
Yeah, it should increase it, right? The more energy I add, the more of that substance gets into the gas phase. And so the more vapor I'm generating, the higher the vapor pressure. And so we do a little bit of math and we get 660, 2 sig figs. We get 660 millimeters of mercury. Okay. 2 sig figs comes from our delta H of vaporization. So we add more energy, our molecules are moving faster, there's a larger fraction of them that can get into the gas phase. As they go into the gas phase, we create more pressure because now there's more vapor up there, and so our vapor pressure increases. So P2, 660 millimeters of mercury. Any questions about that math? Okay, that's the Clausius-Clapeyron equation. We solved it for pressure. We could just as easily have solved it for T2 if we knew P2, or if we didn't know any of those, if we didn't know delta H, but we knew temperatures and pressures, we could solve for delta H as well. Okay. All right, so we talked about how boiling point kind of relates to intermolecular forces and how the strength of intermolecular forces increases our boiling point. Which I'm just going to abbreviate BP, not British Petroleum, but boiling point. And so how do we know what temperature the boiling point really is, right? We looked at that graph that had energy rather than temperature on the x-axis, but we can convert between those two. How do we know when there's enough of those molecules on the high energy side for it to really be boiling rather than just evaporating slowly? And the answer is the boiling point, so the BP, is the temperature where the equilibrium vapor pressure, right, so that pressure that we've been talking about, equilibrium vapor pressure, is equal to whatever the external pressure is. Right, so we think about external pressure usually being 1 atmosphere if we're doing something out on the bench. And so we would need to get the equilibrium vapor pressure up to 1 atmosphere in order for it to boil. That's why sometimes in the baking instructions for your brownies, for example, they say at high elevations, you should cook this at a lower temperature. Well, that's because at higher elevations, the pressure is lower, and the pressure is low enough to change the boiling point of water by a little bit. And so that's going to affect how your brownies or whatever it is bake. Also takes less energy to boil a pot of water in Denver than it does in Myrtle Beach. Notice that there's a little asterisk here for our boiling point. That's the normal boiling point because it's measured at 1 atmosphere, right? So if we talk about a normal boiling point, our external pressure is exactly 1 atmosphere. From this table, it's pretty clear to see which of these compounds have pretty weak intermolecular forces, which have pretty strong intermolecular forces. Argon and methane have boiling points that are negative in the Celsius scale. And argon, of course, is an inert noble gas. He's not going to interact with anybody. Methane, a very nonpolar molecule, doesn't have a lot of surface area because he's so small to have a lot of dispersion forces. Notice that these two have the lowest delta H of vaporization as well. All right. So those 3 measures the equilibrium vapor pressure, the enthalpy of vaporization, molar heat of vaporization, and the boiling point, those three things are really what tell us a lot about how intermolecular forces and intermolecular force strength, how strong they are. Okay. The critical temperature is, so we've been talking about phase changes a little bit, right? The critical temperature is the point at which we can't really go between gas and liquid anymore. It's such a high pressure that the gas and the liquid sort of exist in a constant equilibrium, and I can't change it from one to the other. And so our definition of critical temperature, which is given the symbol T sub C, is the temperature above which gas cannot condense, no matter the pressure. And so it's this temperature that's so large that the molecules have such energy that they cannot, they will not condense back down. And so some things have some pretty high critical temperatures. Some things have pretty low critical temperatures. If we looked at water, for example, right? Water boils at 100 degrees C, but in order to keep water in the gas phase all the time, no matter what, the temperature has to be above 374.4 degrees. Critical pressure, on the other hand, which is P sub C. This table, it says T2 here. That should be TC for critical temperature. The critical pressure is the minimum pressure, so the lowest pressure, that must be applied to liquefy gas at the critical temperature. I thought you just said you can't liquefy gas at the critical temperature. Well, this is the temperature above which gas cannot be condensed, right? And so the critical pressure and the critical temperature form sort of a point where if we are above that temperature, we can't condense at all. But if we're exactly at that critical temperature, we can apply some pressure to get that gas to liquefy. And so those 2 points, those 2 values, the critical temperature and the critical pressure, form a point on our phase diagram. We'll talk a little bit more about phase diagrams on Monday when we're in person. Here is critical temperature phenomenon for sulfur hexafluoride. So here we've got our liquid sulfur hexafluoride. Here it's as a gas. Here is sort of in that stage where it's really sort of a combination liquid gas. You can't make it a liquid, but it's such a high temperature that that it wants to be a gas. And then you cool it back down below that critical temperature. It's a neat thing to see. that point where it's the critical temperature and the critical pressure is called the critical point. And the critical point of CO2 in particular is a relatively easy one to do in the lab, and you can find some good examples of that on YouTube. Yeah. So we've been talking all this time about boiling point and vaporizing molecules, but we can talk about the same thing for solids and liquids. Right? They will not have a vapor pressure, but they still have a molar heat of fusion is what it's called, sorry. Delta H fusion is the energy value. And of course, we have a melting point. Those are the sort of key indicators that we use when we talk about solids and liquids. There's also solids and gases, right? That's delta H sublimation. And there is this deposition temperature, this sublimation temperature that goes along with it. So I'm going to put T sub S there for sublimation. This one is T sub M for the melting point. Okay. All right, that's where we're going to cut it off for today. Monday, we'll be in person again in the Harley Room in the Richardson Activities Building over by the football field. It's not the new indoor arena, and it's not the new Richardson Residence Hall, right? It's the older Richardson building where the weight room and things are for athletes. Okay? If you have any issues, shoot me an email, and I can point out where it is on a campus map. Okay. Have a great weekend. If you're not already on campus, safe travels as you return. And I hope you do well on the quest, right? So quest due at 5 o'clock, should be opening now or soon. And the safety quiz also due at 5 o'clock if you haven't done that yet.
Thank you.
Thank you.
Thank you.